Okay, so I will talk about broadcast reduction and other collective operations. Why that? It's old hat, it's old issues, but I think there are still things that can be discovered, things to do, and all these things have become extremely important in recent years. Machine learning, all this stuff, a lot of that rely on reduction operation, in particular, all reduce like reduction, reduce scatter like reduction. So there's all kinds of good reasons, also if you are more theoretically minded, to look at these things and continue to look at these things. So that's what we will do. And I'll show some algorithm which works on particular communication structures, the circulant graphs, which you may know. I will show you what that is, and very nice algorithms come out for these things. So here's a what-if question. Let's assume that we have some algorithm for the broadcast operation, which I will denote like this, the broadcast from some buffer with a root, and C is our communication network. So some graph which we can communicate. And this buffer from the root should go to all the other processors. Yeah, this is in MPI known as the bcast operation. If we have some algorithm for this thing, then we can probably also do reduction. Broadcast is like this, things go out, and reduction things go up to the root. So at least if our operator here plus is commutative, we can just turn around the communication steps and we can do the reduction operation. Okay, so that is fine. So if we have that, we have that. And also this is in MPI, the MPI reduce operation. We can also do the all broadcast operation, which in MPI is called allgatherv. For some bad reasons, I think we should think of that more like an all broadcast. So that means that everybody has a buffer, everybody is root in a broadcast, and simultaneously we do all these broadcasts together. So if we have this broadcast algorithm, we can also do this thing. But here it gets more tricky. But let's see, we have this algorithm and we try somehow to schedule the communications, overlap the communications, combine the messages which are running around in these broadcast algorithm, and magically maybe we come up with an algorithm for the allgather. And here there's this V, and that means that the buffers that we broadcast from the different processes can have different sizes. Yeah, this is difficult. There's not much good out there in MPI. The implementations are mostly deficient in various respects. And what we will see today is that we come from here to here with a very nice algorithm which covers the V case in an certain sense, in an optimal way. Okay, if we can do that, we can turn it around and do the all reduce. So in MPI, this is called reduce scatter, also for some bad reasons. Think of this as a reduction where everybody is a root in a reduction over the data, the reduce scatter thing. So that we can also do, and we will see that also. And if we can do these things, then we can also do the all reduce, which are here called reduce all. That means that we do a reduction and then we broadcast to everybody. And how can we do that? We just do the all reduce followed by an all broadcast. So this is the old pattern of doing that, and essentially that is also the best that we can do. There are lower bounds that show that we cannot break sort of the bottlenecks inherent in this kind of implementation. Okay, so that's the plan. So we have P processors in this communication network. Let's assume here that we have one-ported communications. That means each processor can be involved in only one communication operation at a time, but in a fully bidirectional way. And that means the processor can send a message to somewhere and it can receive the message from somewhere else in one go, and that's all it can do. Under these assumptions, then we know that we need a logarithmic number of communication rounds in order to complete a broadcast. One process has the data, next round, two processes has the data, 4 and so on. We can only, in the best case, double. So we can never break this bound under these one-ported assumptions. Yeah? If we have more ports, we can do a bit better, but it's still some logarithmic thing. Yeah. Okay, you all know that. If we assume this linear fine transmission cost model, so we have a startup time and a cost per unit that we transmit, then we could possibly do broadcast in these logarithmic number of rounds, so sort of the overhead, and that's just the cost of getting the data out of the root. I don't know any algorithm which achieves that. I don't know any reasons that it is not possible, but that's not what we will do here. We will do something else. We will look at the so-called multiple message broadcast problem, or the end block broadcast problem. So the problem here, or the idea here, is that we have partitioned our buffer into n blocks. We cannot do anything with the blocks. So that's like here, but we have these n blocks, and we want to get these n blocks to all the other processes. Yeah, and here, for sort of the same reason, the bound is that we need n-1 rounds to get the first n-1 blocks out, and then this logarithmic overhead to get the last block down to the last slowest process or whatever. So this is our lower bound. We cannot do any better than that. And this is what we will achieve today, hopefully. So this is sort of the pipelining bound. But what that essentially means is that the processors are working. We have all these blocks running around in the system. And what this says, so in order to achieve this bound, they all have to be busy all the time, receiving new blocks and sending blocks that they have seen before. Yeah. So it's like a kind of the best thing that we can do with pipelining. You get something and you send something else out. Okay, so we will now is green. We will achieve this bound with a particular kind of communication network. Yeah, and if we plug that into the alpha beta model, we get something like that. So we have a logarithmic number of rounds, latencies, and then we have some lower order term, and then we have here we are linear in the size of the buffer. There's no extra penalty factor here. So this is good. This is good, and this is what we have to pay for by doing this pipeline. Yeah. And when we take these algorithms that we will see and we specialize them, we will get also results for the all reduce, so the reduce scatter and the reduce all. So the all reduce, okay, the lower bound says that to do these operations, we have to get, we have our vector of data, we have to get everything except one piece out here. So that is the communication lower bound. We have to do that. And for the all reduce operation, there comes a factor of 2. And there are also papers claiming that this, or showing that this is actually a lower bound. And this is what I said in the beginning, means that we cannot do better than doing a reduce scatter followed by an all gather. This factor 2 is there and we cannot beat it. So that's what we're going to do. Okay. These things have been researched for a long time. So in the 90s and 2000s, there were many papers studying this multiple message broadcast problem. So, okay. So what we will see today, we will try to meet the lower bound for the n-block broadcast problem, and then we get all the other nice things more or less for free there. I'll show that, and then I will show how to specialize these things to the reduce scatter, so the all reduce problem, when the blocks have the same size, and then we get an optimal, and I think this is a new result here, at least I have not seen it, that we pay only the logarithmic penalty, and then we get the blocks, p-1 blocks in and out, and that's all that we have to pay for. The ring algorithm that many of you probably know, and which is very famous these days for all reduce and reduce scatter, has this term, but it has a linear term here. And now we get the best possible, only the logarithmic overhead, but with the same volume complexity. Okay, and when we then combine that to get the all reduce, we have, this is optimal, but we have a factor 2 in the logarithmic latency. Okay, probably we can live with that. So we will see these things. As I said, I have been working on this for a long time. So this broadcast schedule that I will try to show you came up quite some years ago, but with a very large overhead in computing the schedule. And what we will try to indicate today is that we can compute these schedules that we need also with only logarithmic overhead, which is optimal. And that is what we need in order to have an efficient implementation of these things. We cannot afford some offline algorithm to do that. Okay, then there are some more recent results with some log square overheads, and now we are down to logarithmic overhead. Okay, and there are all other papers achieving these things, but with quite different communication patterns, and communication patterns that are for certain reasons not so attractive. They do not allow us to easily make the jump from broadcast to all broadcast. Yeah, and with the pattern that I'm going to use, we can easily make this transition. So we get that for free. Okay, so let's get down to some real work here. So what is this communication structure that we are using? this is what's called a circulant graph, and this looks something like that. We have any number of processors. So this is a good thing here. It works for any number of processors. There are many results for powers of 2, others for 3, or for special kinds of things. But that's not good. In MPI or other libraries, we want something that works for all numbers, any number of processors. And that's what we get here. So we place the processors that we have on a circle equidistantly here like this. So here we have 10 processes. Q is always the logarithm, the base 2 logarithm of P rounded up. So remember that. And then we look at one process and how does it communicate in a circular graph. So it's like that. We have chords in the graph. So these are these skips, which says we can jump 1, 2, 4, 7, 25, some ahead in this circle. And all the processors have the same chords, so the same skips. So we look at this processor. It has an incoming edge with a skip and an outgoing edge with a skip. And then it has certain skips. So here's skip 1, skip 2, skip 3, I guess, yeah, and here's skip 5. And we see for some skips the in and outgoing edge may be the same. That can happen, whatever. So here 1, 2, 3, 5 are the skips in this case, and we will see how this comes. So this is the communication network or communication structure. And the nice thing about that is that all the processes can work simultaneously without any risks of deadlock if they follow the skips in the same order, yeah? So this gets from here, this gets from there and sends there, this gets from there and sends there. They all do the same thing, no deadlocks, yeah, for all the skips. So our algorithms will be like that we in some order steps to the skips. There are Q skips, go through that. If we are done in Q rounds, then we are fine. And for the end block problem, we then go to the Q skips, and then we repeat Q skips, and like that until we are done. So that's what we will do. Okay. The skips here for the broadcast problem are particular. So we compute them by halving and rounding up. So we take our P, divide by 2, round up, divide by 2, round up, divide by 2, round up until we are down. So here, for instance, if P was 10, then we have the skips 1, 2, 3, 5, and then 10. So the last one, yeah. So these are the skips. So there are algorithms, you probably know the block algorithm like that. They also work in the circulant graph. The skips there are powers of 2, 1, 2, 4, 8, 16, and so on. And that means that there are some nasty things at the end if P is not a power of 2. And these nasty things we cannot afford here for the broadcast problem. So that's, we use these. Note here that these skips, okay, we can now, by following the skips, come from any processor to any other processor. That's obvious. But this path that we follow is not unique. That makes things difficult. Yeah, we have to arbitrate and select one path. Yeah, and that you can see already that becomes tricky when we have many blocks going around. We need to be clear which path we have chosen for this block to get from there to there. Yeah, something like that. So they are not unique. 1 plus 2 is 3, and 2 plus 3 is 5. So we can easily see that. Okay, good. I think we will not need that. Let's see. Okay, so what can we say about schedules if we want to broadcast? So the idea is that all the processors sit there in the circular graph, use the skips, they receive something, send something. Yeah. So in order to get this lower bound, it must be like this, that when a processor sits there and receives something and receives a block, it must be a block that it has never seen before. It must get new information in each round. Otherwise, we cannot meet the bound. And when it sends something for correctness, it must be something that it has received before. Yeah. If it just sends something that comes maybe later, then it's broken. So these are our two basic observations. We need to so we will compute schedules for each processor, receive block and send block over Q rounds, which says in round K, what is the block that this processor is going to receive in that round. And for round K, what is the block that this processor already has gotten and which it can now send in this round. Yeah. So we do that for Q rounds. And when we get beyond Q, then we just add Q to these schedules, and then we go to it again. Add Q, go to it again. Add Q, go to it again, until we eventually finish. This can go on indefinitely. We have only n blocks, so we need to do something in the end to get it right. Yeah, but that's not a problem. So that's how it will work. So here's how it looks. So here we have a large number of processors, or medium large number of processors. That's why we have 10 blocks here. Here is a processor. This one sends some skip ahead, and okay. Send and receive blocks must match. That means that when this processor sends this block over there, this must be prepared to receive exactly that block. Yeah, that was condition with one correctness condition, so they must match like this. When we receive something, as I said, all the blocks must be different, and they are different in a particular way. So this is a condition what these colors means. So for the first Q rounds, we have one block, one positive block. That means in this first Q round, sort of the algorithm is warming up. Each processor will get one real block, yeah? And then the other ones are negatives. These are blocks that will start to become active after the first Q rounds, yeah? So in our algorithm, when we see a negative block index, we do nothing, yeah? So what this means is that in the first Q rounds, we go and then we see this positive block, we get it, and then we can start to send it further on. So, okay, that's how it looks. And yeah, here's a concrete example for some number of processors, blah, blah. And there we can see exactly it goes on. Here it receives nothing. They will become relevant in the next Q rounds. Here it receives a round, and we can see it fulfills our condition. The send block schedule is like this, that we start then in the next round to send this block further on. Yeah, this was our basic correctness condition for the send blocks. Okay, last thing is that one processor is special, the root. It's the one which has the blocks. So we construct the schedules such that the root just sends out its blocks greedily. So like this, 1, 2, and 3, and so on. Yeah, and based on this is sort of the condition which fixes exactly how all the other schedules will see. Yeah. So we just pick this greedy thing here, and then hopefully things work out that such schedules exist. But now you can see what, and with that, then in our toolbox we can write our broadcast algorithm. And this does probably not look at all like the broadcast that you know. Yeah, it's a completely symmetric algorithm. It goes to we can see here n-1 plus q rounds, so our bound. This x is just an offset that we need for certain reasons. I will come to that. So this lower bound number of rounds, and what does it do in each round? Yeah, it computes the next processor and the previous processor based on the skips, and then it uses the schedules here to send a block and receive a block. Yeah, and this offset here O is incremented with q after each q round. Then we go to the next phase of q rounds, the next phase on q rounds. So as I explained. Yeah. Okay. Good. So details. I think I mentioned it. If we see a negative block, we don't do anything. That is somehow taken care of in this send receive operation. And when we do only we have only n blocks. Yeah. So at the very last phase, we start to see blocks which have an index which is larger than n. And those blocks which we just kept to n-1. Yeah. So that means in the first round is sort of special. The processor will receive one real block, and then in all intermediate phases of Q rounds, they receive new blocks and send old blocks. And then in the very last phase, they start wrapping up. When they see a large one, they cap it down to n-1. And then after the last phase of Q rounds, the claim is we are totally done. And that's where this x comes from. I choose x such that I always do a number of rounds which is a multiple of q. Yeah, so that the last phase must be full, because the last phase has the task of wrapping up what was going on in the previous phase and taking care of the very last block, this one here. Yeah. Okay, so that's why I have to choose this X, and then we are done. Then we just need to do this to compute the schedules, yeah, and then we can broadcast. And here's sort of the proof, as I indicated, by the condition on how these receive schedules look. In the first Q rounds, the processor will get one new block, yeah, and in all the following rounds, the following phases of Q rounds, they will wrap up from the previous one and get one new thing, and then they go ahead like that. So it's an easy induction based on the condition of on how the receive schedules look. Okay, so I hope you're happy with that. Here's how it works. We saw the constructed schedules. The first one, we get a new block and start sending it further on. And then we get out here and start for the next, in the next phase, and just adding Q, and then it looks like this. Now it gets real blocks, yeah? The blocks that were sort of from the previous phase. Here it gets a new one, which is being set out. And these are new blocks that the processor will get. And we can see here that it fulfills the conditions. Here it gets block 1 and sends it in the next round. 3 sends it in the next round. You can see also here all kinds of weirdness, that it is not really an easy or obvious pattern what's going on here. Here, for instance, we repeat sending 3 in 2 rounds, and here, blocks are swapped. You can see we receive that one and then whatever, and then we go back. So it's not, there's no sort of simple greedy pattern what is happening here. Yeah? So that's sort of the magic here. How do we get these schedules? How do they look? You may know, so the Johnson Ho old papers, how to do things in hypercubes. You can do similar things, and there the patterns of the blocks are quite regular. It's at least easy to see how things work, but here not at all. Okay, we turn it around, we get the reduction algorithm. So you can see, maybe if you are attentive, that the only thing that happens here basically is that I interchange the role of the receive block and the send block, yeah? And then I go from the top down to the bottom, yeah? So I just sort of turn the broadcast algorithm around, and then I have a receive algorithm for n blocks, yeah? Good. Okay, some interesting observations here. If we have only one block, basically this is like a binomial tree algorithm, yeah? So what I claim here is that these algorithms could be good for the whole spectrum of message sizes. If we take the message size, based on the message size, we decide how to split into blocks, and then we broadcast these blocks. If the message size is small, we have only one block, and we are down to what's essentially optimal and binomial tree-like algorithm. And if it's larger, we have more blocks, up to a very large number of blocks. Yeah. Finding the best number of blocks is a non-trivial problem. If we have a simple performance model like the alpha beta model, we can just balance things and we get the square roots and whatever that I show you. But we all know that this alpha beta model is not very realistic. There are a lot of other things playing a role, and so really, given your system, your message size, your whatever, choosing the right number of blocks for doing this is not an easy problem, and that's something that we are working on, and it's partly surely an experimental problem also. Yeah. Okay, and another thing is, so here these algorithms are designed under the assumption that we have a homogeneous system. Everybody can communicate with the neighbors in this circulant graph with more or less the same cost, and that is of course also something which is not does not hold. So if we have a cluster, we need to somehow adopt it to the cluster. But there are many ways for doing this, and this is not the problem here. Okay, allgatherv, so the all broadcast and the all reduce, so the reduce scatter operations. So how can we do that? Yeah, the key here is that all the processors follow exactly the same communication pattern in all the rounds, no matter what. So in order to do the all broadcast thing, we just compute the schedules. So each processor now computes p schedules, one for each, corresponding to each of the other processors being the root. Yeah. he has an array of schedules, so it's p times log p for the size of the schedules. It pre-computes these, and then the allgather algorithm is just the same thing. Instead of just doing what one schedule says, it goes through the p schedules and checks which block do I have to get and which one do I have to send for this corresponding to this process being the root, or that processor the root, or that processor, or that processor. So to solve the allgather problem efficiently for the irregular case where the buffers are maybe different sizes, I just compute the total size. Based on that, I decide on the number of rounds, and then just use these things here. That means that the blocks from the different processors may in each round be of different sizes, but that does not matter. They go through the same number of rounds, and then we can compute sort of that we have time which is linear in the total size of the problem. Okay, so I think this is maybe the first algorithm which achieves that. At least there's not much out there on these kind of problems, and implementation-wise, things are just bad. So they're not doing this. Okay, if we know that if the allgather problem is small, then it's no problem. But if they get large and very irregular, these things may be of interest. So here's basically the algorithm. So I compute these send and receive schedules, and then when I send receive, I have to do for all the blocks for all the processors. So there's a pack step where I go through all the schedule blocks, pack them together in a buffer, do the send receive, then I get blocks back for the next round, and then I go through them according to the schedules and unpack them into their right position. So there's of course an overhead here. It's an unfortunate overhead. We need to pack and unpack before each round, because we don't know these blocks are completely disjoint in memory. Yeah, so we need to do something about that problem. Okay, and we could do the same also then for the reduced scatter problem, and then we get this bound, which is the best we can do under this linear fine cost model. Okay, a bit more. If we now restrict ourselves to just one block, what all this says is that we can do the all broadcast, so the allgather and the reduced scatter in p communication rounds, and only p-1 blocks sent and received. For all broadcasts, so the allgather, this is well known, so you know probably the Brock paper that they do exactly that. But for the reduced scatter, I'm not sure that this is known. At least I have not seen it. So all these things about these schedules, if they exist, they prove the existence of an algorithm for reduced scatter, which achieves exactly that. And that was, at least to me, a big surprise, because we had a paper on cluster last year with a slightly different communication pattern, which is very good for other things. And we tried to use that also for reduced scatter, and there we had a reduced scatter which was not exactly p-1 blocks, but if p was not a power of 2, it could be up to a factor 2 worse. And that disappears with this observation here. And the algorithm is actually very simple, so I will just show it to you. And here it is. So this is reduced scatter. Reduced scatter block. So all the blocks are assumed to have the same size, although the algorithm works also if they have different sizes. That's not the same. So here it is. So I go to here, I compute the skips directly by these halving steps. So I start here with the largest skips, and then I go down by halving. So it's the same thing. Compute the processor to receive and the processor to send, and then I send a batch of blocks between the previous skip and the new skip, and receive the same number of blocks, and then I just do the addition. I start receiving from far away, go here, and then get closer and closer and closer. So you can see here that here I really rely on the commutativity of the plus operator. Yeah, things are in no way contiguous, the things that I sum together. But there are many things in this world which are commutative by nature, so maybe that's not so bad. Okay, we have this, and by combining it with an allgather step, we have here an all reduce algorithm. I call it reduce all. That it is so pretty simple. So this is essentially the Brock thing, and this is what I just showed you before. So this could be of interest. So this is an optimal in communication volume, optimal all reduce algorithm. So p-1 block sent and received here, p-1 block sent and received here. The lower bound says I cannot do better, but I have a log factor here, sorry, a log term here and a log term there, so 2 times log. Maybe one could do better in that, I don't know. Okay, so good. So we can see here how it works. So that is p-1 blocks. I try to indicate it, but here it is. Here are the processors. First, I start from here and half. This is the first bunch of blocks that are being sent down to this one. We add them now, then they get yellow. Then I half it. We have 2 blocks, this bunch of blocks, they are sent down here. I add them together, things get orange. I have now this block here. See, we call these one stays, and I will have to reuse them later on. So this one goes down there, it gets green, and then this one goes down there. I add it in, it gets red, and then I'm done. This is the all reduce, yeah? Good. Okay. An observation here is that this actually works for any skip sequence. As long as I can reach, you following the skips, I can reach any other processor. Exactly, yeah. So this might be another tuning parameter here. If you can afford more than a logarithmic number of rounds, you can choose different skips according to your system or whatever. That may be interesting to explore. Okay, and the complexity, so as we saw, there are exactly p-1 blocks sent and received over the rounds, and I did a logarithmic number of rounds. Yeah? So this beats the ring algorithm. This has also this message complexity or volume, communication volume, but a linear term here. And we have now a logarithmic term, and this cannot be done better. Okay, good. So now comes the second part of the talk, and this would have to be at least as long, but I have to cut it, and I will do that. But I just try to indicate why this might work, that these schedules exist. So this is our big question. These were nice claims. If we have these schedules, we have all these algorithms. Do they exist, and can they be computed? Answer is yes. The old paper of mine showed how to compute them in p log p time, which is of course no good. And what we have now is that we can compute them in logarithmic number of steps, yeah, which is optimal. The schedules have log size, so if we can compute them in that time, this is and if we can do it fast with small constants, it's even better. Then we can afford, when we broadcast, just compute the schedule and do the broadcast. As I mentioned, this paper is quite classical. They consider all these kind of problems, the Johnson-Ho paper, and they show that for powers of 2, these things make sense and it works. And we show here by being greedy that in the circulant graph pattern, which is in some sense a generalization of a hypercube, or at least very related, but for any number of processor, we can do this, yeah. Okay, if we have the receive blocks, then we have trivial by correctness condition also the send blocks, yeah. To get the send block for processor R, we go to R plus skip, so for that round, and look at the receive block schedule for that one, yeah. But that would give us an log square algorithm, and that's not good. So we need ideas for both things. Okay. I have to keep the story very short. So this positive block in the schedule is important. That's the first block that a processor gets. And all things that are happening after that are based on these real blocks that the processors get. So we try to look at how are these base blocks distributed over the processor. So the root starts greedily sending out the blocks. And then we look at how are the base blocks distributed over all these processors. And okay, so this is here what's happening when the root we send out from the roots in a greedy way, following the skips. We get this distribution of blocks here for 20 processors, And if you look a little bit on that after the talk, you will see that there are a lot of regularities and also a lot of irregularities here. Good, we can do this. We don't have to do it because this was takes off p steps, and of course we cannot afford that. So this is just in our mind that we have this sequence of base blocks. So here comes a processor, and it receives a new block in round k, looking at that processor from that processor here. So what we need to make sure is that when it receives from that one, there must be a new block that this processor has not seen in previous rounds out here that this processor here can have received. Yeah. So our question is: are there always enough different base blocks in this sequence of base blocks that we can fulfill this condition? Yeah. Exactly. So what we need is that here, when we receive here, there in this segment here, that must have been at least k plus 1 different base blocks. Yeah. And that turns out to be the case, and the argument is somehow like this. We look at each of the skips. We start at this here, we can count. So here is a skip of 5. This is skip number 3. So we should have 4 different base blocks, 1, 2, 3, 4, and then a repeat. So this is the case here. And we can easily show that when we start from 0 and for all skips, we have k plus 1 different base blocks. And what we observe is that when we slide this window here, when a block here disappears, a new one not in the sequence pops up. So you can do that offline afterwards. Count that we always have 4 different blocks in this segment here. The only exception is if the second skip is 3. We saw that this could happen. This is not always the case. Here we have 2, but sorry, 3 different ones. But here we have only 2. But that can be fixed, so it's not a problem. Okay, the thing is, yeah, we just need to go to a segment of size 4, then it holds, and then so yeah. So basically, this claim holds. There are always enough different skip blocks. And okay, what you have to believe now is that when we search to the skip block to the blocks, following the skips, starting from the largest one and then going down until we find a certain position. If we do that in a clever way, we can find a sequence of q different skip blocks for each of the processors. Yeah, and then we take these q different skip blocks and massage them a little bit so that we have one positive one corresponding to the processor's base block and q minus 1 negative 1 as the claim says. Okay. So here's the algorithm for finding one skip block in logarithmic number of rounds. So we could just go through the skips. And okay, in order to find all the skip blocks, we follow this logarithmic pattern, but we do that in a backtracking way. So when we look at the processor R minus the case skip, we try to find something which is as closest to that point based on the skips that we still have. We find something, and then we take that base block out. Then we go one skip further, find something, take the base block out. So it's like a backtracking algorithm. We go back and forth over the skips. When we find a block, we take that skip out. So we start with q different skips, and at the end we have none left. Yeah, and this gives us the logarithmic complexity. So okay, there are a lot of details here. This is basically the backtracking algorithm. We try to get as close to R minus skip as we can. Yeah, as we can. If we're not close enough, then we recurse, and eventually we get down and see, okay, here is something. This is a base block for R minus the case skip. Then we take it away by just linking it out of our set or our data structure where we have these, so that we never see that block again. And then we go up and try to look for the next one. So it's like a backtracking thing where we check certain admissibility conditions. And the claim is that this takes only log p steps. So in particular, there are only logarithmic number of recursive calls. And this is also not so difficult to see. The argument is the following. So we recurse down, and down there we may find an admissible block that we then take. Okay, so down in recursion, either we have removed a block, or if we come up, if we come back up and have nothing we remove down there, then the block here is still admissible, so we take it. So in each recursion, either at this level we will remove a block, or the block will have been removed at a deeper level of the recursion. So we always remove a block, and then we have start with only q blocks, then we have q steps. Okay, so this is the basic algorithm here. It is not difficult. There's nothing bad here, and it's actually very fast. And that's what we have to do to compute the block schedule. So okay, he says there are most q minus 1 recursive calls, and also the searching here, the backtracking things, the while loop here is not also at most q over q operations. Okay, here comes the dockering that we get exactly the condition that I set on the receive blocks, which is also nothing. We need to compute the base block, and then we do this algorithm, and that's basically all. So here's the main theorem. We can compute receive block schedules that are correct according to what I told you, and then we are happy, and it takes log p steps, and it's actually quite fast also in practice. So good. I will skip completely the send schedule that uses a completely different idea, a more structural approach, looking at this distribution of these blocks. And there are certain cases where we can say, aha, this must be the send block. And then there are certain cases where we cannot say that. And in these cases, I take the receive block computation in. And then the idea of the proof is to show that there's only a constant number of times where I don't know enough so that I have to do the receive block computation. Yeah, so this is a log p overhead, but I do that only a constant number of times. And if I can get that true, then I also have the send block schedule in log p steps. So that's sort of the claim. And as promised, I will skip it. Here are some more indications. You can see them offline. Okay, so the things are happening here, and the crucial thing is to show that this orange is not too many or too bad. Okay, so the claim here is that, okay, I do the receive block computation only constant number of times, and therefore I can do the receive schedule in log p steps. Okay, very briefly, computational things or some experimental evidence. So these are preliminary results. As I said, there's engineering to do to get this really good. So I verified all these claims that I gave, and this holds up to a quite large number of processes. And I think for these kind of things, this is important to do that. Don't trust the proof. Verify the outcome. Okay. So a large machine in Slovenia, we used 200 cores, 200 nodes, I think, and then on our own small cluster, MPI libraries behave very different regarding the collectives. OpenMP is rather poor, but that's what I had on the large machine. Intel MPI and MPI-CH is for certain collectives much better. You probably have a lot of experience. Other libraries, non-MPI libraries, maybe even better, could be. Okay, so here is a broadcast with 200 nodes and one processor per node. So what can we see? So purple and green are broadcast, and we see here for large messages purple and green. So it's not a factor of 10, but 5 or something. So quite a lot margin here. OpenMPI has weird problems. Down with for small ones, it's sort of on par. Reduce, this is blue and orange, also a solid gap here from some point. So it seems that there's some promise in doing things like that. The promise may be relative to OpenMPI, which is quite bad here. But also for Intel MPI, we can tune it and see that there are solid improvements. So that's my claim here. But that's things we are working on. Okay, then I try to put more and more processes per node. These implementations are completely flat implementations. So as I go up with the number of processes per node, things should not be so good. if the libraries have done their job. But we still see that there's a difference, and even if I fill the nodes up completely, I would expect nothing. But we see here that the OpenMPI broadcast is very bad, and our broadcast here is still significantly better. But this must be attributed to the badness of OpenMPI. I'm sorry, this is a public lecture, but I've said it. Okay. Yeah. Altogether, I did some experiments on our own cluster, and here it's more interesting to look at irregular problems. So we have the case where all the blocks have roughly the same size. Then I have a case with noise, so blocks are differing by some random some random term, and then I have the completely degenerate problem where all the data are only in one block with one processor. So this is essentially like the broadcast, yeah. And okay, here's what we see. So I fill up our nodes with processes. Here, the green one is a new one. It is bad for small things. And this has to do with the overhead of the schedule computation. We call that here it's a P times log P overhead. So that is what we see. What we see here is probably the unpack overhead. So this is to be expected. This one we can easily remove, and I just don't show it here, by caching the schedules. So we compute it once, and then we cache it away. And then also subsequent allgathervs will benefit. And it's not only tied to one communicator, any communicator with the same number of processors can benefit from this. So then we will not see this overhead here. This is only once, but this one will probably be there. Okay, here's a slightly irregular instance, same thing. And here's a degenerate thing, yeah. And what we see here is that when the messages get large, the algorithm that they use in OpenMPI is just not any good. So here's I think a factor 100 or something in difference. So things just break down completely for very irregular problems. And that's not what you like. You like to give your problem that you have at hand to the MPI library and expect sort of reasonable performance, no matter what. Okay, what we see here with the green things is that they are relatively independent of the actual problem distribution. Yeah, so that's sort of the thing that we really want from an allgatherv thing, and claim is we can achieve that modular this packing and unpacking. Maybe you come up with some clever tricks how to sort of alleviate that. That would be good. I'm not sure it's possible, but that's what we have. Okay, so sorry for being slightly over time. Summary: we studied this n-block broadcast problem, which is relevant for a lot of other collective operations, as we saw, and we saw how we can solve these problems with explicit schedules, which says what the processor have to do in each round. And my claim is that this is of practical importance also, and then we are looking at that, and I hope somebody will take it up. Exactly, so making this hierarchical for clusters, tuning the number of blocks that you choose, all these kind of things, yeah. And also the same block computation, I'm still not happy with that. I'm sure that there's some other way of doing that, similar to the way that we do I did the receive blocks, that might be nicer somehow. But the important thing on the claim is log P time for receive schedules and log P time for the send schedules. Both are fast, and we can use them for broadcast and all these other things. Good. So end of the talk. Thanks for the attention, and I hope, I guess, it's time for some questions.
For question. Thanks a lot for the very stimulating talk. Yeah. So if you're here, you can just raise your hand directly and ask your question. If you're remote, you can raise your hand virtually and I can unmute you, or you can also type your question in the chat and I will read the question.
I can start with the first question.
Then?
Simple question. So other than the cost of computing the schedules, the cost of storing the schedules, so as far as I understood, the schedules should be stored for each round. Am I right?
No, you're not right. I computed only once, and it's only this so Q log P number of entries. So it's very small. So for broadcast, there's no problem in storing it. But you're right for the allgather and the reduce scatter. There I need to compute the schedule for each process as being a root. So there I have p times log p space for storing scatter. That, you're right, could become a problem. So for very large systems, I don't know. That's a good point. If you start studying these things and looking at how weird these schedules can be between p and p plus 1 number of processors, and whether the root is there or there, it's not obvious that you can reuse the schedules that you have so that you could compact it. You might be able to afford computing the schedules on the fly. I'm not sure. But these are good questions. So when you scale really up, you have to think about this problem. Yeah. But for broadcast and reduce, I think there's no problem. The schedules are just log p, so they're very small.
That's nice.
Yeah.
So maybe one other question. So assume that I have an application with two separate broadcast and or reduce.
Yeah.
And you mentioned that we can that the algorithm is totally the reverse. So can I use the same schedule and the same buffers and everything? So let's assume the broadcast and all reduce are separated in the application. So can I utilize the same buffers and the same schedules and all inverting?
Yeah. So okay, also a good point. So for simple broadcast and reduce, there's no problem. But for all reduce and reduce scatter, yeah. So the schedule that I have computed for all reduce can also be used for reduce scatter. Yeah. And these schedules, so I need to compute them for all processes being a root. So they depend only on the number of processors what I have to do. Yeah. So for any communicator with p processes, I can reuse these schedules, both for allgather and for reduce scatter. Yeah.
Yes.
Was that the question?
Yes.
Okay. But for simple broadcast, I will just compute them on the fly. And also there's no reuse because the schedule depends on who's the root. And I don't know. This is an online thing. Yeah. And the claim is the computation is so fast that it does not make any sense. Yeah. But for all reduce and reduce scatter, as you say, we can do that. Yeah. So there's this discussion about persistence in MPI, and which I don't think much of. Yeah. So these are kind of persistence where the thing that you store depends only on the size of the communicator. So this is in a sense a very productive or reusable form of persistence. Yeah. You can afford to cache them because there's really a lot of cases where you can reuse these schedules. Yeah. So that also may, to some extent, it addresses the space problem that you mentioned. Yeah. If I have many communicators over the whole system, okay, I cache it only once and not with any.
So two questions. Let's go with the easy one. Can you do in place?
Yeah.
Sure, because you have to send it later, right? So if I'm doing a reduce, it's gone when I receive. I receive it, I merge it into the buffer, and then I cannot send the 10 on. So how do I do it in place?
So what do you mean by in place? The MPI in place thing.
Yeah. That's I only have one buffer.
Yeah, I need to allocate maybe some working storage or also, yeah.
But how big is the working storage? Is it guaranteed to not be OFS?
So if I implement this carefully, I only have to have a window of Q rounds. Exactly. So if I have this huge buffer, I only need to working.
So
this much. So, but that is a good question. Also, I have not implemented that. So what I do, I think in my implementation, is I allocate one extra buffer, the full size of the thing, which is not so nice. Yeah? But this is something, and claim is you can get down to a window size of Q rounds. Yeah. So I guess that you can live with.
Q may still be large.
Yeah. If you're talking about streaming, I think this is a different issue.
Exactly.
So that kind of in place, I don't know, because the blocks can be quite out of order. Still, it's only over a window of Q rounds, but inside this window, and so you may have to consider 2 or 3 windows and then see how much out of order things can. Maybe you could do something, maybe not. I have not looked into that, but that's of course a very relevant thing these days.
It's very funny. We have an algorithm that's completely different, gets exactly the same bounds. We only looked at it for all reduce, but it has like a similar ilk. So it's completely different use. We should discuss. Unfortunately, that Daniela had to drop. He's teaching a lecture, so I promised him to channel for him. so he'll contact you afterwards.
Yeah.
My second question is, what about auto-LV? Because now you can.
Also all V.
The interesting thing is the V. I like the V. So everybody's fighting all to all V. Nobody knows how to get the good all to all V schedules.
Yeah, I don't want to jump out of the window here.
Can you do like these? Have you looked at the circulant graphs with all to all V?
Yes, I have. I have some ideas, but I have not pursued it to the. And if you go back to this reduce scatter, the thing I called all reduce scatter. If you take your operator to be just concatenation, you have also all. Yeah. So you can take this algorithm and you have. So you know this book like combining all to all V. So this would be sort of the other way around of doing it. And trivially, you could do also all V there. But of course, you have no control over what happens. If you can do something better or interesting or good with also all V, I don't know. But this is sort of a key thing to look for, yeah. But we get the more or less for free a different way of doing the message combining also all and also all V here also. Yeah. But with no interesting bounds, I think I can say. Yeah.
Just a small question. So your algorithm works for any number of processors, but it's not so obvious how exactly they look. Have you observed that it's faster for some number of processors, or is this another advantage that it doesn't matter so much whether it's a pure
my claim is that it doesn't matter so much, but this is also something that we should look more carefully. So when I test this on and when I try to, so you saw also the benchmarking results there are not for powers of 2. So I try to look at also different normal processes and +1, -1 and see, and then it seems that there's not much difference. Yeah, but it relies completely on having a good MPI send receive. So this bidirectional send receive communication. Yeah, and systems behave weirdly in some cases. So, but this is what we need here. But what I have seen, I think I can say that it does not depend so much on the number of processes. On the number of processes, yeah. But on the clusters, it of course depends very much on where these processes are. But that is a different issue. Anything else? Don't be afraid. Also, those who are online.
Maybe to clarify one thing for me, at each round, you send only one message in all cases per processor?
Yeah. Yeah, so easy. No, it's really strictly this that I receive a message and I send a message. And that's all. And it's like that for all rounds. Yeah. So in the hypercube, or if things are power of 2, you could do it in a telephone-like way that you do like this, which may sometimes be better, yeah, but that does not work here. I need strictly this, but they receive a message and they send a message, yeah. And the claim or the point here is that it's a new thing that they get and they send something old. So in that way we get down to this bound.
So you mentioned that you reduced the bound from log p squared to log p, and
yes.
I'm curious how practical is this? Like, was it so bad in past with log p squared, like for like practical p, like number of processes?
For small number of processes of 10 or 100, it does not make much difference. If it goes up, it makes a difference. So I did some experiments. So there are some archive papers there where I have this. So I did some experiments where I just on my computer ran for all processes. So in some range, did the schedule, and then I summed the total time. And there you can see the difference between the algorithms. Yeah, that it really makes a difference. Yeah. But in the individual broadcast for a moderate number of processors, maybe not so much. But still, I mean, we are also theoreticians. You want to get down to the bound. So the best thing to have, and that I don't have, the best thing to have would be one which is amortized constant time. Yeah? So you in each round, just like that, compute the blocks. I don't think that is possible. At least I cannot do that. So I need log p time to pre-compute the schedule, and then I can do it. Yeah? But I mean, we like that. So I think it's important enough.
this is maybe more of a thought experiment and less of a question. So so you build these circulant graphs for your communication topology, but then of course underneath we have some physical networks. So then the question part is, do you think it's better on certain kinds of network topologies on top of them? Have you thought about that?
The answer is sure, it's better on certain.
Of course, if it matches.
So what I need is a network which is somehow can embed a hypercube. Or I mean, I have log p outgoing or incoming edges, so I need to be able to embed that efficiently. Yeah. So sure, but I have not studied the problem really. It would be very interesting to see on real networks how good you can embed that, or if there are problems. But I have not studied that. But I think it's a very interesting problem. So if you have various kind of flies and all these things for very large systems, it would be interesting to say, okay, I have this circular graph. Can I embed it? Where are the bottlenecks? I don't know. But of course, it's a good question.
Basically, some kind of hypercube you would need to embed.
Yeah, or butterfly or fat tree or something where I can easily have these log neighbors that are close by somehow. So, yeah. But I don't know the details. So, but this is clearly an interesting thing to think about.
And thinking further, if let's say we don't care about point-to-point communication anymore for certain workloads, do you think we would need to design the networks differently so then we can have all the optimal collectives and send something?
Network design is always a matter of trade-off. I don't know. Yeah, I don't know. But this idea of getting rid of all point-to-point and doing everything with collective is of course nice. Many people have sort of proposed and been shot down. But because it turns out, I think that there's always something which you couldn't handle with your collectives. You need some backdoor or some small things that you. But the idea is good. But this is a very big question. Let's agree on that it's interesting. I don't know.
Anything else? Okay, then thanks everyone for being here in person as well for the first time ever, I think. Let's thank you again.